we have seen definition and several examples of metric spaces so far. Today we will begin with some methods of constructing new metric spaces from the known metric spaces. Okay. To start with, let us take a metric space, suppose x comma d, okay, and suppose y is some subset of x, okay, and as usual to avoid the trivialities let us take a non-empty subset. Okay. Then what we know is that d is a function from x cross x to r, right. Okay. Now since y is a subset of x, y cross y is a subset of x cross x, right. Okay. So this function d can be restricted to this subset, okay, right. That is, in other words, if you can talk of the distance between any 2 points in x, you can take the same definition for the distance between any 2 points in y, okay. So suppose I define that function as d suffix y, okay, is nothing but we can say d restricted to y cross y, okay, d restricted to y cross y, okay. Then with this we can say that y and d suffix y, this will be a new metric space. In other words, every non-empty subset of a metric space is also a metric space with respect to the metric which comes from x as a restriction metric, okay. So this metric d suffix y, which is a restriction of d, it is called an induced metric, okay, metric on y induced by this metric on x, okay. Alright. So this is one way of constructing a new metric space, that is, you can regard a subset of a given metric space as a metric space in its own right. Okay. Another method is that suppose we can take two metric spaces x1 d1 and x2 d2, okay. I mean, as a particular, I am not saying that x1 and x2 must be distinct, okay. They can be same also as a particular case. So take x as x1 cross x2, that is Cartesian product. Then as you know that elements of x are nothing but the ordered pairs of elements, that is first element comes from x1, second from x2. So suppose you take any element x in x, it will be of the form, let us say small x1 small x2, that is in x. So this means x1 is in big x1 and x2 is in big x2. Okay. Similarly, suppose I take another element, let us say y as y1 y2, that will also be in x1 cross x2, which is what is x, and so y1 will be x1, y2 will be x2, okay. Okay. And now suppose I want to define what is meant by distance between x and y, okay. So suppose I want to define what is meant by distance between x and y, okay. Then since x1 and y1 are already in x1 and on x1 there is already a metric d1, okay, I can talk of d1 between x1 and y1, and similarly d2 from x2 to y2, and I can combine these two functions in some way so that this new function also satisfies all the properties of a metric. Now there are several ways of doing this, okay. Let me just take one illustration. So dxy, suppose that is same as d1, suppose I define it like this, okay, define this d from x cross x to r is given by d1 between x1 y1 and plus d2 between x2 y2, okay. Now I leave it to you as an exercise to check that this is a metric, okay. That is a straightforward thing, okay, and you will have to use that fact that d1 and d2 are metrics, that is d1 is a metric on x1 and d2 is a metric on x2. Using that you will be able to prove that d is a metric on this x, okay. And again, this is not the only way. I could have also taken d as maximum of these two numbers, d1 x1 y1 and d2 x2 y2, that will also be a metric, okay. And not only that, several other ways of combining, okay, that is, for example, I can take d1 square plus d2 square and take the square root of the whole thing, that will also give rise to a metric. Okay. So there are several ways of introducing metric on the cross product of two metric spaces, okay, alright, and each of this will make this X as a metric space, okay, alright. I think to begin with these examples are sufficient, okay. All that you need to understand is there are several ways of constructing new metric spaces from the already known metric spaces. One is you can regard every subset as a metric space, and also cross product of two metric spaces can be converted to a metric space, okay, alright. Now let us again go to some general facts about metric spaces, okay. So suppose XD is a metric space, okay. We now want to consider some special sets to begin with in an arbitrary metric space, and then we will look at examples in some concrete cases, okay. So suppose let us say A is any point in X, and suppose R is any positive real number, okay. We want to talk about what is meant by various sets which depend on this point A and this number R, okay. First of them is what we will call open ball with center at A and radius R, okay. So open ball with center at A and radius R. Let us fix some notation for this, because this is something we shall be using quite often, okay. So suppose I call that UAR, okay. Now it is clear how such a thing should be defined, because ball means it is a set of all points, we are taking A as a center, so you take all those points whose center from A is strictly less than R, okay. So that is what will be called open ball, okay. So this will be set of all X in X with the property that distance between, okay, A and X or X and X or A, whichever way you write it makes no difference, okay. So distance between A and X is strictly less than R, okay. That is what is called open ball, okay. Right. Similarly, we will define what is meant by closed ball. Again, closed ball with center at A and radius R, okay. Suppose that I denote by BAR. What should be that? Okay, instead of this strict inequality, we will take less than or equal to, okay. So this will be set of all X in X with the property that distance between A and X is less than or equal to R, okay. And the last set in this category, suppose I take all those points whose distance from A is exactly equal to R, okay, is exactly equal to R, then that we will call sphere with the center at A and radius R, okay. So we will say sphere with center at A and radius R, okay. So that is a sphere. So let us give that, I will denote it by SAR, okay, and that is set of all X in X, set of all X in X, so the distance between A and X is equal to R, okay. Now though we have called these things open balls, closed balls, etc., by these words balls and sphere may form some image in your mind, okay, but these sets may not look like that in various metric spaces. They will look like that in the standard metric spaces, but the arbitrary but these open balls, closed balls can have any arbitrary look. Okay. One more thing I should say here, for example, now from the definition it is clear that these two sets are non-empty. Okay, right, because A certainly belongs to this. Okay, because we have taken R bigger than 0, it belongs to here also, but you cannot say anything about this. Okay, because there may not be any point at a distance exactly equal to R from A, so sphere can be empty also. Okay. Sphere can be empty also, but open and closed balls will be always non-empty. Now of course there you might ask why we call that open ball and why we call that closed ball. There is a reason for that. Okay, we shall come to that reason little later. Okay. There is one more thing I should mention here, is that unfortunately this terminology is not very standard. Okay, different books follow different nomenclature for this, because what we have called open ball, in Simmons' book you will see the same thing is called open sphere. Okay, and this is called closed sphere, etc. And in Rudin you will see that the same thing is called a neighborhood of A. Okay, and in some books you may also call this is called open disk, and it is called closed disk, etc. Okay, so when you are reading any book, you just write in the beginning, you see what those definitions are, and then those terminologies are followed. Okay, for the sake of consistency we shall follow this terminology throughout. Okay, this same terminology and this same notation, U for open balls, B for closed ball, and S for the sphere. Okay. Alright. Now let us see some examples, how do these various balls look like. Okay. Let us begin with the simplest case, namely suppose X is a discrete metric space. Okay. Suppose X is a discrete metric space. As I say, discrete metric space is a metric space whose main use is to understand the concepts. Okay. What is the distance here? That is, distance between X and Y is 1 if X is different from Y, and 0 if X is equal to Y. Okay. So suppose now I take any A in X. Okay. And suppose I consider what is UA1. Okay, UA1. Okay. What will be that? It is the set of all points whose distance from A is strictly less than 1. Okay, what are those points? It's only A, because distance from A to A is 0, distance if of any other point is 1. Okay, so this is open ball with center at 1 is nothing but singleton A, right? Okay. If I take a number smaller than 1, suppose half or 1 by 4, it will be the same. Okay, it will be, suppose I for example suppose I take the instead of 1, suppose I take half. Okay, then also it will be the same, right? It will be the same, there will be no change. But if I take, say, something bigger than 1, then it will be the whole of X. Okay? Then it will be the whole of X. Okay, all right. Similarly, you can say about this BA1. Okay, BA1. Why X minus A? Distance between A and A is 0, that is less than or equal to 1, right? So this is X, right? This is X. Okay, all right. And if you take any number smaller than 1, any positive number smaller than 1, for example, what is let us say B A half, it is just singleton A, right? It is just singleton. So if you take any number strictly less than 1, this closed ball with center at A and radius that number, it is just singleton A. Okay, because there is no other point in between. Okay, all right. Okay, and now since that we have considered this number, what is this S A half? Sphere with a center at A and radius half. It will be empty set, right? Because there is no point whose distance from A is exactly half. Okay, right? So that's what I was saying. The sphere can be empty. Okay, sphere can be empty. Okay, all right. Okay, now let us take little more familiar space. Usual R with the usual metric, okay, usual metric induced by, so what is the usual metric? It is dxy is mod y minus x, dxy is okay, and suppose you take A as any real number and R is bigger than 0, okay, R is bigger than 0, then what is UAR? Okay. If you look at a definition, it is the set of all those real numbers, that is set of all x in R such that distance between A and x should be strictly less than R, that is mod x minus A is strictly less than R, okay, right. What is this set? It is an open interval, okay, open interval, which open interval? There is A minus R to A plus R, okay, that open interval, okay, center at A and the length is 2R, so it is this open interval A minus R to A plus R, okay. Okay, and what about this BAR? It will be same interval but the closed interval, okay, because the endpoints are also, because mod x minus A less than or equal to R, so it is A minus R to A plus R, closed interval, okay, okay, okay. And what is SAR? Yes, it is only because it is, you take only those points for which mod x minus A is equal to R, there are only two such points, namely A plus R and A minus R, so it is the set of all just 2 points here, okay, set of these 2 points A plus R and A minus R, okay. Okay. So let me again remind you about my remark, though we have called them open balls, closed balls, spheres, etc., and these words may create some image in your minds, okay, you should just forget that, okay, because the balls may look like any, for example this open ball is just an interval, okay, whereas here it is just a point, okay, so the appearances can be quite different from whatever image these words may find in your form in your mind, okay. Alright. Now since here we have come across some discussion of intervals, let me also say a few things about the intervals, because some of these things we shall require in our subsequent discussion, okay. Let me just say what are the kinds of intervals that you are familiar with. We already talked about this, open intervals, closed intervals, okay. So let me just say a few things about intervals, okay. You know that this is what we have called open interval, okay, that is set of all x for which A less than x less than B, okay, alright. Then this is what you called closed interval, right, where both the endpoints are also included, okay. We can also think of including one and excluding the other, right. For example, it can be open at this side and closed at this side, that is also an interval, okay. Similarly the other way, okay, that is include A and exclude B, okay. All these are intervals, right, okay. What about something like this, A to infinity, okay, it is a set of all points which is strictly bigger than A, is that an interval, okay, that is also an interval, okay. And what about this, is also interval, okay, okay. And then say something like this, minus infinity to B, that is also interval, and similarly minus infinity to B, that is also an interval, okay. And finally this minus infinity to infinity, okay, which is nothing but what we would call R, right, okay, what we would call R, okay, is that also an interval, fine. So all these are examples of intervals, okay, right. But what is the definition of an interval? How do you define an interval?
Set of all points lying between these 2 points.
Which 2 points?
This these endpoints.
But for example this, so you will say this is not an interval, this has no endpoints. R is an interval or not? It has no endpoints, right? Okay. Okay, so have you come across a precise definition of an interval? In fact, that was the reason for going through this discussion. Okay, right? See, which subset of a real line is called an interval? That is the question. Okay? So that definition should include all these possibilities. Okay, when do you say that a subset of a real line is an interval? All right. Okay, now let me give that definition to you now. Okay, that set should have the following property. That is, if you take two real numbers, say x and y, and suppose x less than y, okay, if these two numbers lie in that set, then all the numbers lying between x and y should also be there in that set. Okay, if a set satisfies this property, it is called an interval. Okay, so let us just write down the definition. Okay, let I be a subset of R. Okay, suppose I call that subset non-empty subset R. Okay, then I is said to be an interval if x and y belongs to I with x less than y, this should imply, I said all the points lying between x and y should also be in I. Okay, it is same as saying that the closed interval with endpoints x and y should also be in I. Okay, right. So if x and y belong to I with x less than y, then this interval x to y, that should be contained in I. Okay. Okay. So this is the definition of an interval. Okay, that is, interval is a set, if it contains any 2 points, it should contain all the points lying between those 2 points. Okay. Do all these sets satisfy this property? Okay. Are there any other types that an interval can take, or does it include all the possibilities? Can an interval be of any something else other than whatever types are written there? Of course, a and b can take different values. Okay, that is no, but is it obvious or does it need proof? Okay, I will not go into the proof. Of course, you have to prove it rigorously, and I will leave that proof to you as an exercise. Okay, I will just give you a hint about how to go about this. Okay. Okay. Okay, so this is an exercise. What is an exercise? Let I be a subset of R, non-empty subset. Okay. Prove that I is an interval. I is an interval if and only if. I is an interval if and only if I is of, okay, how many types are there? 6 plus, there are, okay, we have listed some 9 different types of interval. Okay, okay. So if and only if I is one of the 9 types. Okay, open, closed, semi-open, semi-closed, one or both endpoints infinity, that includes all the possible cases. Okay, all right. Of course, that this implies this is trivial. That is what we have seen. Okay, if I is one of those sets then I is an interval, that is clear. Okay. The real proof is required for the when I is an interval to show that it has to be one of these types. Okay. Now my hint is as follows. Okay. That depends on LUB axiom again. Okay. Consider the various cases. I is bounded above, not bounded above, or bounded below, not bounded below. Okay. And again various cases. Okay. That is, this will have various combinations, bounded above but not below, below but not above, unbounded on, etc. etc. Okay. It will cover all these cases. Okay. And then if it is bounded above, then that set must have a least upper bound. Okay. That set must have a least upper bound. Of course that least upper bound may or may not belong to I. Okay. Again that will decide what is the type of the interval. Okay. Right. Similarly look at the greatest lower bound. Okay. So everything will depend on the application of this least upper bound property, and making use of that least upper bound property in various cases you will be able to show that all the intervals are one of these types, one of these 9 types. Okay. Okay. Next question that we would like to know is that suppose you are given 2 intervals. Okay. Suppose you are given 2 intervals and you consider their union. Okay. Will that be an interval? In general no, right. For example, you take the interval 0 to 1 and then take the interval, let us say 2 to 3, and if you take their union, that will not be an interval. Okay. Okay. But instead of 2 to 3, suppose I take half to 3, then that will be an interval. So what is the difference now, what from the earlier 2 sets and these 2 sets? Yeah, these are not this, that is their intersection is non-empty. Okay. Their intersection is non-empty, and this is something that you can prove about any family of intervals. So that I am giving you as a next exercise. Okay. Okay. What is the exercise? Given it need not be just 2 intervals, it can be any family of intervals. Okay. Given a family of intervals whose intersection is non-empty, okay, show that union is again an interval. Okay. So let us write in the usual format. So let us say, let I alpha belonging to some indexing set lambda, I alpha belonging to some indexing set lambda be a family of intervals, such that intersection of this all this I alpha in lambda, that is intersection over the whole family, is non-empty. Okay. That is, there is at least one point which is common to all of them. Okay. Is non-empty. Okay. Then union I alpha in lambda is an interval. That is, of course I have not written prove that. Okay. That is understood. Okay. That is the exercise. Okay. Okay. Now let us go to next familiar metric space, namely R2. Okay. As you know, R2, R3, etc. you can have various types of distances. Let us begin with the most familiar case. Let us say you take the distance which comes from, which we had called d2, okay, the so called Euclidean distance. Okay, that is given by the norm suffix 2, that is d2 xy is norm of y minus x, and where this is norm suffix 2. Okay, right. And we will take A as the origin to begin with, A at 0 0, and let us take R as 1 as we had taken in the earlier case. Okay, and suppose you take this UA1, okay. So it is a unit ball with center at A is this origin and radius 1, is origin and radius 1. Okay, so what is this by definition? It is the set of all points such that distance between x and A is less than 1. Okay, so that is, let us say it is set of all x in R2 such that distance between x and a is, suppose if x is x1 x2, then distance between x and a is nothing but x1 square plus x2 square and the square root of that whole thing, okay. So that is less than 1, x1 square plus x2 square, its square root is less than 1 is same as saying that this itself is less than 1, right, okay. Okay. So this is nothing but usually what you would call a region enclosed by the circle, okay, a region enclosed by the circle with the center at the origin and radius 1, okay, which is inside, excluding the points which lie on the circle, okay. That is the reason why some books call this disk with the center at a and radius 1, okay, is more popular in complex analysis books, okay, they will call such sets as disk, alright. And what is BA1, okay, only thing here it will be less than or equal to 1, okay, and that will be nothing but the region enclosed by the circle including the circle itself, okay, including the circle itself. And what will be SA1, it is, now we want those points where the distance is exactly equal to 1, that is nothing but the circle, right, that is nothing but the circle, okay, okay, all right, okay. Now instead of R2, if you take R3 with again the same distance d2 which we call Euclidean distance, okay, then that will be set of all x for which x1 square plus x2 square plus x3 square is strictly less than 1, okay. So that will be the region enclosed by the sphere with the center at 0 radius 1, which is what will look like a ball, okay, that is what we normally call a ball, okay. So if you take R3 with the usual distance given by d2, that is Euclidean distance, then the balls, all balls look like ball and sphere looks like sphere, okay. Now let us make a small change here. For example, in R3 open ball with center at origin and radius 1 will be open ball, and this closed ball will the one which will also include the sphere, and the sphere will be just the set of all points which are exactly at a distance 1 from the origin. By the way, in these spaces R2, R3 etc., when the center is 0 and the radius is 1, those kind of balls are called unit balls. For example, this is called open unit ball, okay, open unit ball. Open unit ball means what? The center is the origin and the radius is 1, okay. Similarly, closed unit ball means it is a closed ball with center at the origin and radius 1, and similarly unit sphere means sphere with the center at the origin and radius 1, okay. Now what we shall do now is that we will just make a small change here, okay. Instead of taking this distance given by d2, let us take the distance given by this d1, okay, right. What is d1? d1 will be this suffix 1, okay, that is mod y1 minus x1 plus mod y2 minus x2, right, okay, all right. So suppose now I look at UA1, it will not be this because this is not distance, it is mod x1 plus mod x2 mod x1 minus 0, that is same as mod x1, so it will be mod x1 plus mod x2 less than 1, okay, and similarly this will be set of all x in R2 with the property that mod x1 plus mod x2 less than or equal to 1, okay, alright, and this last thing will be set of all x in R2 with mod x1 plus mod x2 equal to 1, okay. Okay, so how will these sets look like? Okay. I think it is easiest to look at this first. Okay, once we fix this, all the others are easy. Okay, so let us say this is the origin, okay, and look at this mod x1 plus mod x2 equal to 1. Okay, you have to make various cases, x1 bigger than, both are bigger than or equal to 0, both are less than or equal to 0, okay, or one is bigger than 0 and other is less than 0, etc. Okay, let us start from the beginning. Suppose both are bigger than or equal to 0, okay, then mod x1 plus mod x2 is nothing but x1 plus x2. Okay. So that is nothing but x1 plus x2 equal to 1. Okay. So set of all those points for which x1 plus x2 is equal to 1. Okay. What does that represent? It is a straight line. Okay. It is a straight line passing through the points 1 0 and 0 1, right. Okay. It is this straight line. Okay. Okay. All right. Now take another case, suppose x1 is positive and x2 is negative. Okay. Okay. Then this will become x1 minus x2 equal to 1, sorry, this one, x1 minus x2 equal to 1. Okay. What will that represent? Okay, it will be, okay, so this is minus 1 0 and this is 0 minus 1, and similarly looking at the other two cases, for example, if both are negative, it will be x1 plus x2 is equal to minus 1. Okay. So it will be passing through this point, okay, these 2 points. Okay. So this will be the sphere. Okay. This will be the sphere with the center at 0 and radius 1. Okay. All right. And once you decide what is the sphere, then what will be the open ball? It will be nothing but the set of all points which lie inside this, right, excluding the points on the boundary. Okay. And similarly closed ball will be all points lying on these as well as the points inside. Okay. Right. Okay. All right. So the open balls, closed balls, etc., their appearance and will depend on what exactly is the metric. Okay. Is that clear to you? Because since you will be using these concepts very often, so I am spending some time on this. Okay. Now let me give you an exercise. Okay. Similarly draw the picture of these spheres. Instead of taking the distance d1, take the distance d infinity. Okay. Okay. Do similar things for R2 with d infinity. What is d suffix infinity? Of course it is norm y minus x suffix infinity, that is nothing but maximum of mod y1 minus x1 and mod y2 minus. So what will be the changes here? Instead of this mod x1 plus mod x2, you will get maximum of mod x1 mod x2. Okay. Then see how the whole thing looks like. Okay. Then see how the whole thing. Okay. That I will leave it to you as an exercise. Okay. We will just see one more example and then we will go to more general theory. Okay. Let us look at this set C0 to 1. Okay. We have seen that is a set of all continuous functions on the interval 0 to 1, and we have taken the distance here d suffix infinity. Okay. Let us take this distance d suffix infinity, it is nothing but norm of f minus, okay, d suffix infinity of between f and g is norm of f minus g suffix infinity. Okay. Remember this is what we have called soup norm. Okay. Soup norm is supremum of mod fx minus, that is norm of f minus g is supremum of mod fx minus gx, where x is in 0 to 1. Okay. All right. Now suppose I take some function, let us say f, it's let us take for example fx is equal to, okay, let us say fx is equal to x square, some function like this. Okay. So that is an element of this. Okay. Let us also draw a graph. So how will that look like? It is a function. So this is the point 0 0 and this is the point 1 1. It has to pass through these 2 points and it may look something like this. Okay. Okay. All right. Now suppose I want a ball. Let me take closed ball. Okay. Closed ball with center at f and let us say radius, let us say half. Okay. Does not matter whether you take half. Okay. What is this by definition? It should be the set of all those functions whose distance from this given function g is less than or equal to half, okay, right. Let us write it, okay, that is, this is, suppose this is our metric space X, okay, it is the set of all those functions g in X such that distance is this d suffix infinity, such that norm of f minus g suffix infinity is less than or equal to half, okay. Alright, now can we describe it in terms of graphs? Okay. Suppose there is a function g, okay, and let us say its graph is something like this, okay, its graph is something like this. What is the distance between f and g by definition? Yeah, but how it is defined, okay?
At each point we take we consider the set and take the suprema of
yeah,
that
each point you consider the difference fx
yeah,
minus gx, okay.
yes.
Suppose this is difference, okay, this is difference, okay, and so you take the suprema, in fact in this case it will be maximum because it is a closed bounded interval, okay. So the maximum difference between fx and gx should be less than or equal to half, okay, maximum difference between fx and gx should be less than or equal to half, okay, alright. Now what will be the geometric way of describing all those functions in terms of graphs? Okay, for example let me just take these two functions, suppose I take f1 of x as let us say x square plus half, okay. How will the graph of that look like? This same thing will be shifted above, okay, okay, suppose this is half, so let us say this is f1, okay. I will similarly consider f, let us say f2 of x as x square minus half, okay, is nothing but it will be shifted below, right, okay, alright. Now suppose you take any g whose graph lies in this, strip, okay, take any g whose graph, then will it follow that the distance between f and g must be less than or equal to half, right, okay. So in this case closed ball with center at f and radius half is nothing but all those functions whose graph must lie between these two graphs of f1 and graphs of f2, okay, right, that will be the closed ball, okay, closed ball, okay. But what about sphere? Suppose I want a description of a sphere with the center at f and radius half, what will be that? Yes, or let me be more specific, will the sphere consist of only those two functions f1 and f2?
nothing like that.
Does everybody agree with that? Why? So, suppose I take a function like this, yes, at this, see the distance is the supremum, okay, so distance between such a g and f will also be half, okay. So sphere, so in case of sphere what you will require is that you take those functions whose graph touches at least once one of the functions f1 and f2, okay, not just these two functions, okay, all those functions whose graph meets the graph of f1 or f2 at least once, those will be the functions which are included in the sphere, okay, okay. So if you look at this example you will see that the so called balls and spheres, they can have practically any arbitrary shape, okay, in various metric spaces, okay, alright. I think this is enough to begin with as far as examples are concerned. Let us now proceed a little further with the theory. Okay. So let us say we again have a metric space x and d. Now what we want to consider is the position, let us say given a subset, okay. Suppose A is a subset of x, okay, and let us say we take some point, suppose I call that point A in small a in x, okay. This point may or may not belong to A, okay, we will consider in general case, okay. We shall say that this point A is an interior point of A, that is what we want to define. Okay, so we will say A is said to be an interior point of A. Interior point of A if you can, if let us say if there exists some real number r bigger than 0 such that open ball with center at A and radius r is completely inside A, okay, is completely inside A, okay. So such that ball with center at A and radius r is inside A, okay. This obviously means that the point A also is inside A, okay. So every interior point is a point of A, okay, right. Suppose we collect all such points, okay, that will form a set, okay, that will form a set. That set is called interior of A, okay, that set is called interior of A, okay. It is the set of all interior points of A. Okay. For example, let us take the set R with the usual metric, okay. Let us take R with the usual metric, okay. Yes. Oh, right. This should be open ball. That's right. Open ball. That is right. Open ball with center at A and radius R. So that should be U, okay. All right. So coming back to this example, so suppose I take the set A as something like this, okay. Suppose I take say 0 to 1, okay. Now suppose we ask what are the interior points. Of course, remember, since every interior point must be a point of every interior point must lie inside A, we can forget about the points which are outside A, okay, right. For example, this point 1 is not in A, so that there is no question. So coming back to the points say 0 to 1, so suppose we take some let us say we take some point, let us say x belongs to A, then 0 less than or equal to x less than 1, okay, 0 less than or equal to x less than 1. Let us forget about 0 for the time being, okay. Suppose I take this point 0 less than x less than 1, 0 less than x less than 1, then can we say that every such point must be an interior point, okay. And how does that follow? Because suppose this is 0 and that is 1, and if I take any point x here, okay, I can always find, because we know that the ball with center at x and radius r, we already seen that ball with center at x and radius r, that is nothing but the interval x minus r to x plus r, okay. So the whole question is, can we choose r such that the interval x minus r to x plus r lies completely inside A, and the answer is obvious. You take x and 1 minus x, take minimum of that and take any positive number which is less than minimum of these two, then for that r this interval x minus r to x plus r will lie completely inside A, okay. So every such x for which 0 less than x less than 1, that is an interior point, okay. Okay, now which point is left out? The point 0, okay. Now is that an interior point, and why? Again, why is not an interior point? Because whatever r you take, open ball with center at 0 and radius r, that will be the ball of the form minus r to r, okay, that will be the ball of the form minus r to r, and every such ball will contain some point which is outside, A, okay. So this is not an interior point, 0 is not an interior point, and rest all are interior point. In other words, interior of A is this open interval 0 to 1, okay. In this case interior of A is nothing but the open interval 0 to 1, okay. Okay. Is that clear? Okay. All right. What about suppose I take this set n, set of all natural numbers, what is the interior of that? Interior of that is empty, right? Interior of that is, because there is no interior point for that, okay. So interior of this n is empty. What about interior of Q? Yes, again empty set, right? Interior of the set of all rational numbers is again an empty set. Suppose you take the set of all irrational numbers, again empty set, okay. Because again, because of the same thing which we have seen, between any two real numbers there exists a rational numbers, okay. So if you take any interval, that interval has to contain at least one rational number and at least one irrational number. So if you take simply the set of all rational points, its interior is empty, and similarly if you take the set of all irrational points, its interior is also empty, okay. I think we will stop with that, we will continue with this in the next class.